This will be a lecture about waves in the ocean, and I called it From Whale Songs to Tsunamis to indicate the large extension of these waves in the ocean. So whale songs, that's acoustics. That means very short wavelengths, couple of centimeters. Tsunamis are the very long waves that have wavelengths of several hundreds of kilometers. So we will make our way through this series of lectures by first an introduction about the general physics on waves. Most of them are valid also for other waves like electromagnetic waves or shock waves in rockets. So we have to get some knowledge about the basics. Then we will move to wind waves, which are very prominent when we have a look at the sea. Everybody associates waves in the ocean with wind waves, but there is of course more. There are the tides and tsunamis that we will have a brief look at. Tsunamis are free long waves, tides are forced long waves, and we will see what the difference is. Then we will go to inertial waves and also have an overview over acoustics in the ocean. In order to have waves, we need oscillating systems. And an oscillator changes periodically its state, like this weight here, which is attached to a string. Actually, such an oscillator has also an equilibrium state somewhere where it is at rest. And only if we apply some energy to it or input some energy to it, like pulling on this weight here, pulling it downwards, and then let it go, then there is a restoring force, in this case here of the spring, which wants to bring the weight back to the equilibrium state. But then due to this high velocity that it will have, it will overshoot and move to the other side, to the turning point, until it is decelerated by the spring, and then again it will move back. So it will change between having high potential energy at the turning points and high kinetic energy when it passes the equilibrium state. So here we see that in motion, and we just can describe this extension, the displacement here of this weight by the formula given here. So the vertical displacement, zeta, Greek letter zeta, as a function of time can be described by the sine of, in the argument we have the time t again, and it depends on a period which is given as tau. So we have here the description of the symbols that we use. So it will be sine of 2 pi for full cycle over the period tau times t, and then we have a certain amplitude that depends on how far we pulled this weight before it started to swing. If we go to waves, then we just have again oscillators that are coupled to each other, so that the energy that we have added to one oscillator will spread to the next neighbor oscillators and then will spread over space. And accordingly we will describe this again with a formula. So here the displacement depends also on the horizontal dimension. We have now a sine shape that would also depend on x, and the characteristic number would be here the wavelength, the length of a wave. So waves, at least mechanical waves, can have two forms. So waves, mechanical waves can have two forms. They can have can be transversal waves, or they can be longitudinal waves. And the difference between the two is that in the upper panel, transversal wave, and the lower panel here, the direction of the displacement is perpendicular to the direction of the wave propagation. While for longitudinal waves, the direction of the displacement is in the same direction as the propagation of the waves. So typically, transversal waves would be the surface gravity winds caused by the wind on the ocean, and longitudinal waves would be acoustic waves. Now let's look at an example that are, for instance, surface waves that we can find in a pond. So the equilibrium state that we would find over here, where the sea surface is undisturbed, can be described by our well-known hydrostatic equilibrium that you know from other lectures. So we have an equality of the pressure gradient, the vertical pressure gradient. So this is just an equation for the vertical component. And the vertical pressure gradient is in equilibrium with the gravity, g times the density. So here we have the variables, P is pressure, rho is density, G is gravity. Now, if energy is added to this equilibrium by someone splashing the water with his or her feet, then we would cause this water to oscillate, or rather to spread waves. And so we need another term in our equation here. In the vertical, we have an acceleration of the water. So we have here dw over dt. W is the vertical velocity, so we have an additional term here. And since the surface is coupled by the pressure and the velocity term, the oscillation would not just remain here, but it would spread in the form of waves. The waves spread in all directions, as we see here, so that the wave fronts would be circular, and we see here the wave crests. Here we see, so the energy of the disturbance moves away. It will be transported away with the gravity waves. The energy input could be anything. We can throw a stone into the water. It could be a sudden wind gust, or it could be an earthquake. And we call the resulting waves free waves. These free waves will travel with a frequency that is inherent to the system. So the waves decide, or the medium decide, which would be the frequency that this is traveling with. I've been speaking about energy being transported. So let's have a closer look here. What is transported where in a surface wave? So you see here in blue the wave surface and how the phase of the wave is transported in this direction. Now, while one wave length is transported through this image here, we see the according motion of a particle of the water surface. And we do see that this is transported in a circle. And so it is sitting or remaining at the same place. while the wave phase is moving to the right. And actually it fulfills a complete cycle when the wave is passing for a full wavelength. So you can read that up here again. So in a surface wind wave, a passer follows a cycle, an orbital motion typically during a wave period. So if we look at this without motion, again here in this sketch, so the seagull would represent a water parcel, and while a wave crest is approaching, it would be moving upwards until the wave crest is passing underneath the seagull when it is at its highest point, and in the back of the wave the seagull would move downwards and complete a full cycle, reaching its deepest point in the wave trough. So that illustrates an important property of waves. They do not transport any matter. The material, the water remains in place, but waves transport only energy. Okay, let's have a look at some basic terms that we need to know. We have seen already the period, tau, given in as a Greek number tau, measured in seconds. It's the time between the passage of two wave crests or other phases. The reciprocal of it would be the frequency, typically given as f, which is then 1 over tau. The number of crests passing for a certain time. And sometimes we are also seeing the angular frequency if we want to write it in this way. And then a full cycle would be given by 2 pi over tau again, and then we would name this angular frequency omega. We have the same for the spatial dimension, where we have the wavelength given as Greek lambda as the distance between two successive peaks or two successive other phases of the wave. The reciprocal would be the wave number, denoted as kappa, 2 pi over lambda, over the wave length. And from these two we can obviously derive the phase speed, denoted as c, which is the ratio between the wavelength and the period. Or we can also write it as the ratio between the frequency and the wave number. And the dimensions would be meter per second. Then we have the velocity of the particles that we denote as u for the horizontal velocity, w for the vertical velocity. And then we have the wave height. Actually, we do not use typically the wave amplitude, although down here we have the sinusoidal wave, but we would rather define a wave height. So it's the vertical distance between the crest and the trough. And the cause of this is that not all waves are sinusoidal. Some of them might have very different shapes, and then it would be difficult to describe the vertical dimensions of a wave with the amplitude. So the wave height is distance between crest and trough. And then we have a parameter called steepness. So you might think the steepness would be defined here by the slope, but it is not the case. The steepness is the wave height divided by the full wave length. So we have seen 3 waves so far, which means that the waves are excited instantaneously by a splash of these feet, for instance, and then they can propagate freely and oscillate with their eigenfrequency, which is a frequency inherent to the system. Of course, we can also force waves continuously. So if an oscillator is forced periodically with a frequency f, forcing frequency f, then the system will oscillate with that frequency of the forcing and no longer with its eigenfrequency. And in this case, we speak about forced waves. That might be, for instance, sound waves. When I speak continuously, I continuously force sound waves. The surface waves can be forced by a persistent wind. And we would have, for instance, also tides that are periodically forced by the motion of the celestial bodies and the Earth. Waves can be modified in various ways. They can, for instance, be reflected if we have a wall here, so that a wave propagating in this direction, here we see the wave front, would not be able to pass across this wall here. So it would have to change the direction, and a wave that is reflected, here we see the wave propagating back into the same half space that it comes from. Then we have refraction. Waves can be refracted. That means again that their direction is changing. So you see the wave fronts over here, and the wave is propagating in this direction, while over here the waves are propagating in this direction. And obviously the waves are coming from this side here, and they change the direction. And they do that because of a change of the phase speed. So we will soon see what that means. Waves can be diffracted. So we have a irregular pattern of waves out here in the open ocean. And when waves arrive here at the entrance to this bight, then passing this, they would occur as wave fronts that are circular. So here the waves would, from this opening, spread radially in all directions, so that perpendicular to the propagation we have these circular shapes of the wave crests. And they might be superposed and interfere. Interference we have when waves are superimposed that have the same wavelength and same frequency. So again, here we have waves arriving from the open ocean. Again, we see here the wave fronts. So we see that the wavelength is the same. When they have to pass a series of islands with gaps in between, so the waves that pass here through these gaps, they will again, behind this gap, radiate in all directions, and so that the wave fronts now are curved. And if they meet with the wave fronts from a neighboring opening, then we will find locations where the wave fronts will be superimposed and be twice as large as the original wave heights. And typical patterns would appear that are then called interference patterns. So why is that so? I have just described what happens without explaining it. All these modifications can be explained from a very nice principle that a Dutch astronomer and mathematician has formulated. And he has derived the principle of elementary waves. So Huygens was a scientist in the 17th century in the Netherlands. And what he formulated is that each point of a wavefront can be seen as origin of an elementary wave, which propagates at the same speed and wavelength as the original wave. Such an elementary wave spreads in all directions, making a circular wavefront. And then he says, each wavefront can be thought of as an envelope of all elementary waves. Now, what does that mean? If we look at the sketch down here, we see wavefronts, parallel wavefronts, straight lines, arriving from the left side here and approaching a wall. This thick black thing should be a wall, which does not allow the wavefront to pass to the right side of the wall over here, except at this gap. And when this part of the wavefront would arrive here at this gap, it would provide energy that can pass through the gap, and this wave energy would then, of course, excite a wave here that will then radiate and spread in all directions. Why should it not? There is nothing else to prevent it. And accordingly, then circular wave fronts will occur. And the first one would be this circle here. And this is called an elementary wave, right? And we can imagine this gap to be very, very small, and then just a point source of a wave would occur here by the energy transported by these waves. So in elementary, here we see an elementary wave. Now we can of course imagine that we have several gaps over here. So again, here we have our wave fronts as straight lines, and now the wall has several gaps, and through all these gaps, part of the energy can pass and develop another elementary wave. So we have an elementary wave over here, and we have an elementary wave over here, and so forth. Now, if we look at the outermost first wave front that has passed, then we can see that we can connect it, and this is called an envelope of the wave fronts, and it looks already rather straight over here. So if we continue to have more gaps in the wall until we have no wall anymore, but just only gaps, then we can imagine that we have just a continuous series of elementary waves that are excited at each point here. And if we make a connecting line of all the envelopes of all the wave fronts here, then we see that we end up again with a straight line. And so now we have found an understanding for what Huygens said. He said each point of a wavefront can be seen as origin of an elementary wave. That was this case here. And each wavefront can be thought of as envelope of all elementary waves over here, right? So with this nice principle, we can actually explain all the phenomena that we have seen on the previous slide. So we can look again at the reflection of a wave. We have said that we have a wavefront here, and you see now that the wavefront at a certain instant meets the wall. And so at the wall, we have just learned that everywhere new elementary waves would be created at a wavefront. So at A here, when the wavefront hit the wall, elementary waves would be created so that energy cannot pass the wall, it has to go back. So an elementary wave would be radiated here from this point A, and we can see here the one of the wave fronts that corresponds to the elementary wave at A. Meanwhile, the original incoming wave has continued and touches the wall now over here, and again new elementary waves would be created a little later, so that when we now connect the wave fronts from this elementary wave, from the second one and from the third one, we would get a straight line that is tilted in this way. So this would be the new lined wave front from the reflection. As a composition, as we can see over here and even more over here, from a series of elementary waves that have been excited at the wall by the incoming wavefront. So if we would define what a reflection is, we could do it this way. Reflection occurs when the wave travels to a medium where it cannot penetrate or cannot fully penetrate. Of course, we can have part of the wave passing here. Still, we would get partly reflection. So the wave returns to the half space where it comes from. Sometimes in the exams, when I ask what a reflection is, students answer they turn back to the origin, the waves, but this is not true. We see, of course, that the direction is a different one. So we can derive this from the elementary wave concept, and we can do that also for the diffraction. We said we have irregular wave field outside here. Some of the waves or part of the waves can pass this gap here. At the gap, elementary waves will be created, and so these can then continue into the bay here and spread radially so that the wave fronts are circular. So diffraction occurs when the wave meets a boundary with a small gap, and since everywhere along a wavefront, so also at the gap, elementary waves are created, these elementary waves propagate in all directions in the bay. Again, we can explain it using the elementary wave concept. Same for the refraction. So we have again two media, A, where the waves propagate in this direction, and I said they change direction. We can see that here, and I said that this is due to the change in phase speed of the waves. Now that's a little difficult to explain how that works, and actually I use for the explanation not a wave, but a nice image of toy cars. So this is now not waves, but toy cars, but they illustrate very nicely what happens when the speed of a propagation changes from, say, a fast speed to a slower speed. So this is a toy car that goes in this direction, and here it is rolling on a hard ground, so it can roll quite fast. So we have a fast medium here, and then it meets a carpet, and here we have a line between the slow and the fast medium. And you can easily imagine when the car arrives here, it will first arrive with the right wheel that will go on the carpet and feel the slow motion, so it will be slowed down, while the left wheel is still on the hard ground and is moving faster. And you can immediately imagine that then the direction of the car will change towards the perpendicular towards the perpendicular on the interface between the carpet and the hard ground, the two media. Actually, you know that principle from optics, where refraction is quite a common phenomena, and all the explanations that are given for in optics with a slower speed of the electromagnetic waves of the light apply here as well. So there are different ways to explain it. If you look at the definition, refraction occurs when the wave travels from medium A into a medium B that implies a different wave speed for whatever reason. And then the rest is just to explain in which direction the propagation will change. So let's have then a final look at the interference, which is again based on elementary waves that pass through gaps. Here we have a series of gaps, as we said. Our waves fronts here arrive at these gaps. At the gaps, elementary waves will be excited, and they have all the same frequency. So they will be curved here, have curved wave fronts, as we have seen before. And since they have the same frequency and the same wavelength, they will, the wave crest, for instance, will superimpose here and have particularly high wave crest, form high wave crests here at the points where they add up, and at points of wave troughs, they will be particularly deep. And so we will get a regular pattern that is called interference pattern. So interference is a special case of superposition. We add or subtract waves when they come with the same frequency, and then pass these gaps. Okay, so again, we can derive this from the concept of the elementary waves.